So let's start with EEEE lecture number 32. So today we are going to start with the application of diode, and one of the application of diode is its use as a rectifier. So diode application, which is rectifier. We'll also see where it is rectifier useful. Now in this rectifier, we'll be studying three topics, three types of rectifiers in it. So first will be half wave rectifier. Just write down the types of rectifiers. Half wave rectifier. Then we'll have full wave rectifier or full wave center tap rectifier. And then you will be studying about full wave bridge rectifier. Okay, so what we need to do, we'll discuss about all of these. I'll write the common points which we are going to discuss. For all these types of rectifiers, we are going to analyze it. So first of all, we will see its circuit diagram. Then we'll see how it works. Then the input-output waveforms with respect to time. Okay, then we'll analyze the rectifier circuits. What do you mean by analyzing the rectifier circuits? I'll explain. Analyze. So in analysis, you will find average output voltage, V out average. Then you will find V out RMS. Let me highlight it over here. Or you can even find I out average or I out RMS value. Then the third parameter which we are going to find is rectification efficiency. Rectification efficiency, which is termed as eta. Okay, how good is the rectifier will be determined by rectification efficiency. Then you will find ripple factor. The amount of AC content present in this output of rectifier is the ripple factor, denoted by, you can call it as small r. And the last will be TUF, transformer utilization factor. Right now I'm not writing the full name. This is what you will do. Okay, so for all the rectifier circuits, first the circuit diagram, it's working, input output waveform with respect to time. Then in analysis, you have to derive the expression for V out average, V out RMS, or I out average, I out RMS, rectification efficiency, ripple factor, and TUF. You don't have any numericals for it, but derivations are there in exam. Is that fine? Then completed this much. Then after the rectifier, you will also study about, and also one more thing, all these rectifier circuits you will be doing with only resistive load, which is the simplest. So you will be doing the analysis only with R load. Okay, resistive load, only resistive load is there in your syllabus. And then in addition to rectifiers, you will also study filter circuits. So in filter circuits, you will only use capacitive filter. There are actually three types: capacitive filter, inductive filter, and inductive capacitive filter. We will be studying only capacitive filter. Okay, understood what we are going to cover. We'll require around 3 to 4 lectures to cover this topic. So that will conclude your module number 4.1 if we complete the rectifiers part. Understood? Now let's start with the concept. Understood what are the topics which we are going to study? Overview, and this is how you should study for each rectifier circuit. Point number 1 to 4 you should know. Okay, and study one of them correctly, others will come naturally to you. Okay, so let's start with the concept. Where are they used? I'll show you all one this thing. Okay, can you see this power supply block diagram of DC power supply? This is the same block diagram which we have shown in the mobile battery charger. So first of all, you have this AC voltage. Now this is from a foreign auto book. That's why they have written 120 volts, 60 hertz. In India, we have 230 volts, 50 hertz supply. So all their devices, if you go in some European country or foreign Western country, you will see that they use a lower power supply at the input. Input side AC power supply is less. So they consume a lot of power in the AC generator only. So this is my AC signal. Then this is my power transformer, or you can say a step down transformer in our case. And this step down transformer will step down this voltage. Then we have this diode rectifier. So we have to study this block. What will the diode rectifier do? It will rectify the negative part will be gone. You'll get this type of waveform. Let me show it to you. Can you see these waveforms? Ultimately, what we want is from this AC, we want what? We want at the output a DC signal like this. This AC to DC conversion. Okay. So this is what happens all in your adapters, your mobile phone adapter, your charger of your laptop. It happens this way only. You're connecting it to a socket, and when you connect it to a laptop or your mobile phone, you get a DC voltage and current, DC current. So this is the process, and we require a filter to smoother down the contents of the output. Then we require a regulator so that all the fluctuations are removed, and we will get a DC output. Okay. Now in a syllabus, we have in detail rectifier part. We don't have voltage regulator and filter part, only one. Okay. Now you understood why studying this filter rectifiers and filters are important. It's a part of a AC to DC conversion process. Okay. And in everyday life, we are using your chargers. All the chargers have this process. All right. Now let's go back to the topic. So for this, you require some basics of the diode. So write down. So whenever the diode is forward biased, now this is the symbol of a diode. We can represent the voltage across the diode as positive, negative, VD. And how does the current flow through the diode? Diode name is D. How does the current flow through the diode? From left to right. Only in one direction, that is ID. Now, when the diode is forward biased, this diode will behave as if it is a short circuit. Okay, so this diode will behave as if it is a short circuit, like this. Now, why we do this? Because the voltage across the diode, when it is on, it's around 0.7 for silicon diode. So 0.7 voltage, when we compare it to 230 volt, it's very less. So that's why we assume it to be very, very small. This is one of the assumptions. So diode is reverse bias, it's represented as a short circuit. If it is on, or we can say forward bias or on, then whenever the diode is reverse bias, it is off. Now reverse bias by its current is very, very low or negligible. How do you represent zero current? By showing open circuit, right? So when a diode is reverse bias, replace it with open circuit. Okay. So this is an approximation. Don't confuse with it. So these are the diode basics which we'll be using. For forward bias, we short circuit it, and for reverse bias, we open circuit it. With the help of this, we'll be able to understand the rectifier circuits. So are you all ready to start now, everyone? So write down, first of all, half wave rectifier. Write down the heading, half wave rectifier with R load. Okay, I'll explain you fundamentally what it do. Okay, in terms of a black box. So let's say this is my half wave rectifier. I'm calling it short form as HWR, half wave rectifier. What is the input to the half wave rectifier? Let's say it's coming from the output of the transformer. So my input is AC. Correct? This is versus time. So what does the half wave rectifier do? At the output, yeah, please be quiet. At the output, you get this waveforms, right? As input. So you will get only half wave getting selected. Only during the positive half cycle they are active, and during the negative half, it will be zero. So the waveforms you will get is something like this. During the negative half, it will be zero. Again, during the positive half, you will get it will follow the input. So this is what you mean by a half wave rectified output. First of all, why half wave? Because in the full cycle only half wave is working, and on the remaining half the diode is off. Okay, this is the basically the funda or the crux of it. This is how it should expected output should look like. Half wave rectifier with resistive load. All right. Now let's draw the circuit diagram of it. So first is my circuit diagram. Now you have to show the circuit diagram in terms of your transformer, and then you will be connecting step up or step down transformer. Step down. The number of turns are less over here. Then this is my diode element connected over here, and here is my load. I'm using a resistive load, so I call it RL, and this is my output. Okay, this is AC mains, and how much is AC mains? Single phase, 230 volts. Single phase 230 volts, 50 hertz. Now, this is my step down transformer. What is the function of a transformer? To step down the AC voltage. What is the other function of the transformer? To isolate the input from the remaining part of the circuit. That means this transformer is isolated, this ground and this ground, they are separate. Are you understanding what I'm saying? So it will prevent you to get, if you are touching the other part of the circuit and your transformer is on, you won't get this off because the grounds of both are different. Are you understanding? If grounds are same, what will happen? The current which is flowing over there might interact with the remaining part of the circuit, and it will, whoever is handling it may get a shock if they are not careful. Is this okay? Fine. Now, this is my diode T. Now let's say that input of this, output of this transformer, we call it as VI. VI. Okay? So what is VI? Tell me. VI is sinusoidal, right? So VI will be Vm sine omega t. Agree? How does this VI look like? This is omega t. This is my VI. This is Vm. And this is minus Vm. So for the positive half cycle, this I consider as a positive cycle. And the other one, this will be negative half cycle. And it will repeat itself. What will be this? This will be pi. This will be 2 pi. And it will go on repeating. It's a periodic AC signal. What is VI called as? VI is called as the secondary voltage of the transformer. Secondary, write it down. Secondary voltage of transformer. Okay, that means if V in is 230 volts, we have a step down transformer with a ratio of 10:1. What will be VI then? Example, VI will be around 23 volt AC. All right. If you have a step down transformer with a ratio 10:1, it will step down the voltage 230 to 23. All right. So Vm and minus Vm will be around somewhere around that 23 volts. Now let us check how does this operate now. Everyone has drawn the circuitry, understood what are the parameters. Now let's start. Ready? So this is my positive half cycle. This is my negative half cycle. When the input is negative, it's negative half cycle. Input is positive, it's positive half cycle. Remember one thing, when Vi is positive, it's in the positive half. And when Vi is negative, it's a negative half. So Vi is negative entirely or Vi is positive entirely. Okay? Diode does not allow current in negative direction. So remember that also. Yeah. Let us see first case. So write down case number 1. Please, if you're not writing, please be quiet. I am requesting once again. So in the first case, we can write during the positive half cycle, during positive half cycle of input, what happens? So diode, we have this diode. Let me call this diode as D1. Can we say diode D1 is on during the positive half cycle, right? During the entire positive half cycle, let's say the diode turns on instantaneously. You doesn't even require 0.7 volts. It turns on when as soon as we apply positive voltage. So diode will turn on during the positive half cycle. Agree? Because you have positive over here, negative over here. So we are forward biasing the diode. So we can say during the positive half cycle, D1 is forward bias, that is on. When D1 is forward bias, how does it look like? How does the circuit will look like? What I told you, when a diode is forward bias, what will happen? Replace it with a short circuit, right? Here we have the resistor RL, and here we have the output V out. Here we have the AC mains. Here we have VI plus minus VI. Will the current flow in the circuit? Yes. Current will flow, it's a resistive load. So that current flow, I'm calling it as I out. This is my diode. So this is my diode T1, which is on. Okay, and we are assuming that the voltage across the diode is almost zero. So it almost takes negligible current, negligible voltage to turn on. Alright, now tell me, during the positive half cycle of VI, what is my V out? Tell me from that diagram. My Vi is over here, and if the diode is on, it is short circuit. What is my V out? Same as Vi. Correct? It's a parallel thing, right? So output is equal to Vi. That means output follows input voltage. Okay? During the positive half cycle. This happens during the positive half cycle. Acha, tell me what will be I out? I out will be equal to, a simple Ohm's law, na? This is a resistor, this is voltage, so it will be V out upon RL. What is my voltage across the diode? This voltage across the diode will be approximately zero. So this is the summary happening in the positive half cycle. Did you understand? Now similarly, we have to go for negative half cycle. Okay, listen very carefully. Can I start? Negative half cycle. Okay, so write down case number 2. During negative half cycle of input Vi. Achha, what is Vi? Is the output of the transformer, remember. Is the secondary output of the transformer. So negative voltage means what? This green color. Positive voltage, positive half cycle means this yellow. Okay? I hope you are remembering. So this is green. And this will be yellow. In terms of the representation of colors which I have given over there. Okay. Now tell me what will happen if the diode is off. Just now we have discussed. When the diode is off, it does not conduct any current. Current through it is zero. How do you represent zero current? Open circuit. So wherever you see the diode, represent it as open circuit. Okay. So now draw the circuit again. So we can write over here that the diode is D1 is reverse bias. That is, it is off. Please don't write RB over here. I am writing for short form. You write diode is reverse bias. Full statement. Therefore, it is off. So now if I draw the circuit again, how will it look like? If they ask this question for 10 marks, explain the working, then you draw all the diagrams. If they ask for 5 marks, just draw the main diagram and explain. That's it. No need to draw this again. So this diode will be replaced by open circuit now. We have this RL, load RL, and here we have AC mains. The secondary voltage is VI, and this is my V out. So tell me, will the current flow in the circuit? Tell me first, if there is a break, will the current flow in the circuit? So I out is 0, correct? What about V out? V out is basically I out into RL. So this will be 0. What about the voltage across the diode? This is tricky. What about the voltage across the diode? See, there are two ways of doing it. Diode is reverse bias means what? You connect it in a negative half cycle, right? What about the voltage across the diode? Is it 0? It's not equal to 0. Later on in the analysis, we'll find out why it is not equal to 0. So because you will understand with the help of waveforms. Alright? During a negative half cycle, diode voltage is not equal to 0. So here you will explain the term, which is called as PIV rating of a diode. So remind me when I discuss the waveforms. PIV rating of the diode is called as peak inverse voltage. The most negative voltage a diode can withstand without breaking, going into breakdown. Okay? Now, are we ready to draw the waveforms now? Everyone? Yeah. So let us summarize what we have done mathematically. This is understood. Forward bias, output is equal to input, output follows the input. In reverse bias, output is 0. Straightforward. Now draw the waveforms, input output waveforms, write down. Input, output, waveforms for half wave rectifier, okay? And they are drawn with respect to time. So, first of all, let's write V out is equal to Vi, which is equal to, what is Vi called as? Vm sin omega t, correct? And it is 0. Now, what is the period we will write over here? See now, see the diagram. From 0 to pi, can we say we are in the positive half cycle? Are 0 to pi, we are in the positive half cycle. So output follows the input over there. From pi to 2 pi, it's 0. So let us write. So output is equal to V in or Vi from 0 to pi. And from pi to 2 pi, it's omega t is 0. So this is my mathematical definition of whatever I have explained so far. Let's call this equation number 1. Okay? This means positive half cycle, this means negative half cycle. Now let's draw the waveforms. You have written this. So for drawing the waveforms, you leave some space vertically. Okay? So what I mean is this. Draw it together. So first is my input Vi. So let me draw it. It should look like a sine wave. Huh? Don't draw any triangular wave or any other waveform. Okay? This is omega t. These reference points are pi, 2 pi, and 3 pi. You have to draw the other waveform with reference to this. Okay? So when you draw this, you can use a scale and a pencil, no problem. So see to that this are same. Are you understanding what I'm doing with dotted line? Okay. Now tell me, I am plotting output V out. How it will be? Tell me, this is positive half cycle, so it will follow the input, right? So in a negative half cycle, what will happen? Output is 0, so it will be 0 like this. Okay? And during the positive half cycle, it will repeat itself. So these will be the waveforms of output. And here D1 is on. You can write D1 on. D1 on. Got it? And this will be Vm. Now, if you want to draw, next if you want to draw current waveforms, how will you draw? Will current waveform nature will be same? Yes. Why? Why current nature and voltage nature is same? Because it's a resistive load. In a resistor, current and voltage do not have a phase difference is zero. Okay? So if I want to draw I out, I'll extend it over here. It will be of the same nature, but what will be the difference? Can you anyone tell me? Same nature. But this height is V out upon RL. Are you understanding? Or Vm upon RL, we can say. Said that height ka magnitude ka difference, it's a current, it's a voltage. Okay. Now, the most crucial thing, if you have drawn this, if you can draw this on your own, then very good. Draw the voltage across the diode. I'll give you 1 minute, draw the voltage across the diode. What I mean is this. If I extend it over here, I want to draw voltage across the diode T1. So during the when it is on, VD1 is 0. So no problem in understanding over here. This will be 0. This will be 0 over here and 0 over here. What will happen in the negative half cycle? So let's go to this again. Now tell me what is VD1? Same as VI. And it's in the reverse cycle. Matlab output VD1 is following negative input. Are you understanding? So what will happen is, what is the negative input? Like this, right? And what is the maximum voltage it will reach over here? Minus Vm, right? So matlab, this is the maximum reverse voltage a diode can take, minus Vm. That is what is called as PIV rating. And for a diode, this PIV rating is Vm. Minus Vm, sorry. Understood? Maximum peak reverse voltage a diode can withstand without breaking down. It's PIV rating. So diode has to withstand a voltage of minus Vm. Matlab, let's assume Vm is 100 volt. And in the negative half cycle, the voltage across the diode is minus 100. So it will break down. So you have to select the diode which have a higher rating, higher PIV rating. Following? Yeah. So these are the waveform which are expected. Well, VD1, this is for your knowledge. Even if you draw input, V out and I out, that is sufficient. VD1 was to explain you what is the PIV rating of a diode. Understood now? So these are half wave rectifier input output waveforms. Write it down. Half wave rectifier input and output waveforms. And what is here we call it IM. What is IM given by? Vm upon RL. Remember that. I out is V out upon RL, right? Completed up till here. Now I will tell you what we will do next week, a recap of next week. So write down this circuit diagram, working, input output waveforms are completed just as we have done over here, right? Just I've explained over here, right? First, second and third point are over. Next, we will derive the expressions of all of them. So write down analysis, okay, of half wave rectifier. So analysis means derive first expression for V out average. Derive the expression for V out average. Then second case, derive the expression for V out RMS. Okay. Then we'll derive the expression for rectification efficiency. which is eta. D. Next we will derive for the ripple factor. Expression for ripple factor R. Finally, we'll derive the expression for transformer utilization factor, TUF. And this has to be done same way for all three rectifiers: half wave rectifier, full wave center tap rectifier, full wave bridge rectifier. And most probably one of them will definitely come in exam, because there is for module number 4, these are the topics only. 4.1 में से either they can ask you PN junction or they can ask you rectifier part. So this is what you have to do it similarly for all the rectifiers. I'll do it for 2 of them, and actually for full wave bridge and full wave center tap, most of the derivations are same. So listen, next time we'll start with these analysis for half wave rectifier. So that's it for today.